All right, I'm going to go ahead and introduce the speaker today. It's Martin Lebrat, and Martin is one of the most active young scientists in the field of quantum simulation using cold atoms on optical lattices. So as a graduate student, he did work with Tillman Esslinger's lab on spin and particle conduction through a quantum point contact. And he's continued now as a postdoc in Marcus Greiner's group in Harvard, continuing to do interesting many-body simulations using ultra-cold atoms in lattices, and most recently a triangular lattice, or a type of triangular lattice. Doesn't look triangular, but it apparently is. And they see geometric frustration. So it's very exciting times in this field, and really we'll enjoy, I've enjoyed today talking with you and look forward to your talk.
Thank you, Randy, for the introduction. Can everybody hear me? Yeah? Yeah, thank you for inviting me today to present some of the work I've been involved in recently. That has been very exciting. So today's talk is going to be about the quantum simulation of quantum phases of matter using ultra-cold fermionic atoms. And when I say quantum phases of matter, I don't mean anything totally out of the ordinary. I'm sure most of you have seen a quantum phase in your everyday life, namely magnets that you can find in your kitchen are a typical example of a quantum phase of matter. Although, let me just remove this. Okay. There is a cursor on the screen.
The what?
Oh.
Oh, the pointer.
Ah, the pointer. Okay. Oh, okay. Yeah. That's good. Okay. Sorry. Yeah. Thanks. Yeah. All right. All good now? Yeah. Thank you. So magnets are a manifestation of the quantum nature of electrons in such systems that conspire together in order to create an overall microscopic field that you can use in your everyday life for very, very practical purposes. And so you can really see it as a demonstration of quantum emergence coming from an assembly of quantum particles. Why is that interesting in general? Well, the thing is, although single quantum particles are relatively well understood, say if I take an electron which can have two spin states up and down, its state is going to be described by Hilbert space of dimension 2, which is pretty easy to describe and to describe theoretically and to analyze, including the effect of interactions between many quantum particles is a difficult task because the typical number of configurations that describe such a quantum state is going to diverge exponentially in the number of particles. And so that exponential divergence makes it a challenge to describe from first principle using classical computers, and also makes it interesting to study theoretically using some interesting tricks. But leveraging these many-body interactions to create interesting quantum phases of matter is a chance in order to create materials which have interesting properties, and eventually harnessing these many-body states of matter is paramount for implementing the future quantum computers that can perform tasks more like faster, certain types of tasks faster than classical computers. Now, if there is one iconic quantum material relying on the interaction of many electrons that has been like overall like a big open question and challenge in modern physics, it is cuprate materials. So essentially, the structure of cuprate materials is quite simple. It can be essentially described as a layered material where electrons are essentially evolving on two-dimensional layers and hopping between copper atoms on these layers. Okay, more problems. Is this recording?
I think it was. I can still see the audience here. Okay. Can somebody on Zoom say if they can hear us?
Yes.
Yep.
Okay. Perfect. But now. All right. So yeah, cuprate materials, although they are simply, can be simplified as essentially two-dimensional electronic systems, researchers at IBM in the 1980s showed that surprisingly at anomalously high temperatures, these kind of materials could behave as superconductors, namely materials with a zero electric resistivity. And this superconducting phase of matter is not the only one that is interesting in these kind of materials. Here is plotted a phase diagram of this experimental phase diagram of these cuprate materials as a function of temperature as well as hole doping, or essentially what's the electronic density inside these two-dimensional layers. And essentially it features a wealth of interesting, strongly correlated phases that are insulating or conducting with very peculiar features. And despite the very complicated structure of this phase diagram, it is thought that a lot of the phenomenology of these materials can be captured by a simple model, namely the Hubbard model, which I will elaborate on later on, but essentially contains two main terms, a kinetic term and an interaction term. And the interplay between these two terms is leading to a very rich phenomenology that hasn't been fully understood from the theoretical point of view. Of course, cuprates are not the only interesting, strongly correlated material that might be described by Hubbard-like types of model. More recently, it has been shown that magic angle twisted bilayer graphene and other so-called moiré materials can feature very unconventional phases of matter, unconventional superconductivity in a phase diagram that looks very similar to the phase diagram you have that have been measured in cuprate materials. And so now the biggest question is to know whether these materials can be described pretty well by the Hubbard model, as well as whether how do these strongly correlated phases of matter emerge from the microscopic ingredients that make up this Hubbard model. And so to answer that question, maybe from an alternative point of view, instead of looking at condensed matter systems, I've been looking in the past 5 to 10 years at cold atom systems, which are realized in tabletop experiments, where essentially electrons in this kind of strongly correlated materials can be replaced and simulated by the behavior of atoms that are moving in optical structures, optical crystals of light. So maybe to give you a sense of scale, ultra-cold atoms can be only useful to simulate quantum many-body systems, provided that they are cooled down to very low temperatures. The reason for this is that the average distance between atoms in a dilute cloud is typically a few comparable to a micrometer, which is maybe 4 orders of magnitude larger scales that what you encounter, in condensed matter materials. Atoms are also 4 to 5 orders of magnitudes heavier than electrons. And if you do now some dimensional analysis, it means that the typical energy scales you need to cool your atoms down to is of the order of microkelvins in order to probe quantum effects in such artificial materials. That might seem challenging, but over the last 20 to 30 years, there have been a wealth of atom physics techniques, laser cooling, techniques that have been implemented to cool atoms down to such temperatures. And here is a small video of like a crucial part of our cold atom experiments, namely a magneto-optical trap, where atoms are essentially created inside an ultra-high vacuum chamber, loaded in this case at the intersection of 3 pairs of beams that are near resonant to these atoms. And you can see now these atoms fluorescing at the center of the chamber and being cooled down, in this case, to temperatures comparable to the millikelvin range. And so further cooling techniques allow you to then ultimately probe these quantum effects on the microkelvin range. So what makes atoms very, very advantageous to look at many body systems is the fact that due to their intrinsic diluteness, you can manipulate them using light, which has wavelength of the micro, which is comparable to the density of the atoms. And so one very exciting technique that has been probed in the last 10 years, implemented in the last 10 years, is so-called quantum gas microscopy, where atoms are loaded and probed under a higher resolution microscope objective, which allows you to probe and control atoms on the single particle level. Moreover, it is possible using certain atomic species, such as lithium-6 atoms, which is the atomic species I've been working with, to very, very nicely tune the magnitude of both the magnitude and the sign of interactions between atoms. So interaction between atoms is typically of the van der Waals type, but using some resonance effects to molecular bound states between pairs of atoms and tuning the energy of that bound state related to 3 fermions, you're able to probe both attractive and repulsive effective interactions that are very short-ranged and are useful to implement, among other things, this Fermi-Hubbard model. So Fermi-Hubbard models are one thing, but in the last 20 years, many models relevant for condensed matter have been implemented, relevant for superfluidity, superconductivity, disordered systems, Anderson localization, magnetic phases of matter, topological phases of matter, as well as supersolidity. But yet, and I think I'll try to convince you in this talk that there is a lot of work that can be done to expand the toolbox of cold atoms in order to more closely match what can be realized in condensed matter experiments and gain more insights on such systems. And so namely, there are maybe 2 main ways to expand the cold atom toolbox. From maybe a condensed matter perspective, what you can do is to probe different types of quantum materials and expand, the types of crystal geometries you could look at using atoms. For example, looking at crystal geometries where interactions between the atoms might be frustrated, or even implement like more exotic types of topological insulators. But also you can work on the observable front and essentially implement all the techniques that have been used over the last 50 years, even more in condensed matter experiments, either transport properties, spectroscopic probes, or scanning probe microscopy. So these are fronts that are like really, really active fields of research right now in the cold atom community. And so in my talk, I'm going to essentially divide this presentation into 2 parts, really showing you, and that's work I've been involved in during my postdoc, how you can expand the toolbox in terms of quantum materials to generate frustrated geometries. And this is work performed during my PhD, how you can use cold atoms to probe transport properties. And so more in detail on the experimental side, I will show how you can probe new phases of matter, frustrated phases of matter in lattices, as well as looking now from the physics point of view, how exotic 1D properties can emerge from a very, very small mesoscopic quantum wire. So these are really 2 surprising phases of matter that took us by surprise when we observed them in the lab, and I'm pretty excited to also try to share this enthusiasm about these new phases of matter today. So about these frustrated phases of matter, so in order to understand, what's going on, you need to understand a bit better what this Hubbard model is. In the lab, it's realized by loading ultra-cold atoms, so namely, again, lithium atoms, into optical lattices. And I'll develop on these optical lattices later on, too. These ultra-cold atoms can be using microscope fluorescence using fluorescence imaging and being able to locate each atom individually into that lattice. And again, we are aiming at, in square geometries, implementing this Fermi-Hubbard model and try to describe the properties of cuprates.
Martin, on an image like that, on the previous slide, how thick is it in the transverse direction?
Along the imaging line?
Well, how long along the axis that's coming out of the screen?
We are here loading atoms in a single two-dimensional layer. And so it's essentially a 2D system.
It's just a monolayer.
It's a monolayer, yeah. So on the square lattice, this Fermi-Hubbard model is written as a Hamiltonian that contains two terms. First is a tunneling term that describes how atoms can be hopping between different sites of a lattice. And there is also an interaction term, U, that describes the energy penalty you have to pay for two atoms to occupy the same site. So two atoms now being described as a spin up or spin down, which are encoded into the hyperfine state of the atoms we are populating. In terms of phases, in the very peculiar limit where you have exactly one atom per site, which is called the half-filling limit, you have a phase transition as a function of temperature from a metallic state at temperatures above this on-site interaction energy to a low temperature phase when temperature is below the energy, where essentially atoms are not able to hop on top of each other, and you have exactly one atom per site populating the lattice. And that phase is called the Mott insulator. But having density ordering as here is not the end of the story. It doesn't mean that the entire system is frozen in terms of spin degree of freedom. Namely, there is a third energy scale that you can write down as a function of this tunneling and this interaction energy, which represents the amplitude at which it is possible to flip, to exchange two spins of opposite sign with neighboring lattices through a second order process. That energy scale is called the spin exchange, denoted by J, is proportional to tunneling to the square and divided by U. And essentially, it defines a third energy scale, which in usual conditions is smaller than the interaction energy, and below which, in terms of temperature, you start to have antiferromagnetic order in a square lattice, where each up atom is occupying the odd sides of the lattice, each down atom is occupying the other sublattice. And so in normal experiments, what you do is to essentially take some snapshots of both the density and the spin distribution, and from an average of these snapshots, being able to measure spin correlations between every two pair of sites in the system, and essentially as a function of temperature, see long-range antiferromagnetic ordering spreading over the entire system.
Martin?
Yeah.
How do you have access to spins and not just charge that spin?
So
Actually, could you repeat the question?
Yeah.
I'm speaking, but for the audience.
Sorry. Yeah. The question is how to image spin density distributions in a quantum gas microscope. So in this kind of snapshots, what you typically do before performing fluorescence imaging is to illuminate the sample with light which is resonant to one of the two hyperfine states, which kicks them out of this two-dimensional layer and essentially allows you to look only at the remaining spin.
Thanks.
Yeah. And so one of the main challenges now in the field is to try to reach temperatures that are low enough, compare the spin exchange energy to see these kind of phases. And there has been a long way to this kind of results, including very nice experiments performed in Randy's group about 8 years ago, using other observables to probe the antiferromagnetic order.
So what is the new temperature? You actually see order?
We actually see order, and
what is the new temperature then?
the temperature that
What is the ordering temperature?
The ordering temperature is of the order of J, the spin exchange energy.
That's very high. But
yeah.
Isn't it 0 in 2D?
Oh yeah. So maybe one one caveat here. So in order to see true long-range order, so there is no long-range order in 2D due to Mermin-Wagner's theorem. Yeah, so what we call long-range order is maybe a misnomer here. We see order which is long enough to cover our entire system and have spin correlation length which is greater, say, than 10 sites. So it's not true long-range order, but it's order that's large enough to be able to, like in our finite size system, to see a full checkerboard pattern in terms of antiferromagnetic correlations.
Can you actually introduce anisotropy? Like in the real materials, there's always spin-off coupling.
Yeah.
Can you actually introduce that in your system?
So we can introduce some anisotropy in the tunneling between different directions, and I'll come to that maybe when describing optical lattices. Spin-orbit coupling is maybe a different story and it might be a bit more complicated in our systems. Okay. So I've told you so far about the square lattice, where these cooling down atoms to very low temperatures translates into, let's say, an antiferromagnetic spin order, a spin like state. It turns out that this vanilla square lattice might be an oversimplification of actual 2D materials. If I were to really plot, say, the expected, or maybe what theorists think might be the phase diagram of the Fermi Hubbard, it turns out it would look like this, where here the two sides of the panel correspond to either positive doping, so adding more particles compared to Hafling, or removing particles from Hafling. On the contrary, it is known that in experimental materials, the phase diagram looks a bit more asymmetric. And in particular, I mean, I've shown here many phases in this theoretical diagram with question marks. It is, like, as far as I know, still a debate whether there is actually high temperature superconductivity, D-wave superconductivity emerging from the vanilla Fermi Hubbard model. But maybe there are two features that really distinguish the theoretical phase diagram from the experimental one. First one is that doping is highly particle hole asymmetric in real materials, whereas in square lattices are actually particle hole symmetric. And due to that particle symmetry in the square lattices, it turns out that the vanilla square lattice strongly favors antiferromagnetic order. Which is a feature that might not be again reproduced in actual materials. And so now, how do you engineer lattice models in order to get rid of this strong antiferromagnetic ordering? One way to do that is to actually depart from square lattices in order to introduce some what is called geometric frustration. And that can be easily seen on the case of a triangular lattice, where essentially it is impossible to populate the three corners of a triangle with spins ups and down while having all three spins being entire aligned to each other. That kind of triangular lattice is actually relevant for actual condensed matter materials. So in particular, organic salt has been seen as a candidate material for being an implementation of these triangular lattices. And overall, these triangular lattices have been, and frustrated geometries have been very interesting and have generated a lot of theoretical interest due to the possibility of very exotic phases of matter, such as spin liquid phases at half filling in the triangular lattice. And away from half filling, the fate of these phases is even more unclear. Some work has been hypothesizing some topological superconductivity, for example. And here I'm showing two recent works, but of course it's like a very, very narrow selection of the entire literature that has been produced about geometric frustration and strong correlations. So now, how do you implement geometries beyond the square geometry in the lab? Maybe let me tell you exactly how we create optical lattices in reality. One way to do that is to take laser beams and to reflect them against mirrors in order to form standing waves. Now, if you, typically, in order to create a square lattice, experimentalists take two pairs of such beams that are orthogonal to each other, and that's maybe one subtle element. They choose the frequencies of their lattices in order to be detuned from each other, so that they have some finite offsets, some finite detuning. And as a result, you can really see this superposition of these two lattices as a non-interfering superposition of lattices that create lines like 1D lattices along the horizontal and vertical direction, leading to that kind of pattern. Experimentally, you can also actually do some interference potentials using two beams that have exactly the same frequency. And they are due to some constructive and destructive interference effects. You're actually going to go to generate different types of square lattice, which is a more diagonal lattice with a larger spacing, which is rotated by 45 degrees. And these kind of lattices have been the point of like a 2-year experimental upgrade we have successfully implemented a few months ago, which is quite challenging because you need to be technically very good in order to phase stabilize these two beams related to each other. And so now, what's the point of generating these very fancy but kind of boring-looking diagonal lattices? Well, now if you combine not only two lattice beams but 3 of them, you can actually achieve many different types of lattice geometries. And for example, you could generate structures that are band structures that are very comparable to graphene, and that's something that has been implemented and pioneered in Tillman Essinger's group at ETH Zurich, where they have been able to see Dirac points and generate some kind of topological insulator there. But you could also imagine, not only creating static band structures, but also tunably going from one band structure to another in order to say, for example, go from dimer configurations to square foot configurations that could be useful like down the line for performing the adiabatic preparation of very low entropy states. So it has both like relevance for quantum materials, but also for cooling down the line. So now back to the triangle lattice. How do we do that? Well, it turns out that, we don't use yet 3 lattice beams. We are relying on the two interfering beams I was telling you about. And starting now from this square rotated lattice geometry, which is essentially hosting a Néel order when you bring in antiferromagnetic correlations. You can essentially change the power, the intensity of one of the lattice beam in order to tune it into something which looks more like 1D-like. And by doing so, you're essentially lowering the potential barrier between the sites that are across one diagonal of the square lattice that's pictured on the left. And so by doing so, even though you don't go to a fully spatial triangular geometry, you essentially implement some effective triangular connectivity that is what you need in order to look at triangular Fermi-Hubbard models. So you can really see that potential on the right as a kind of a stretched triangular lattice that behaves like a triangular lattice. And so now, as you're changing continuously that anisotropy, you can create fully frustrated triangular lattices. The anisotropy in such systems is essentially parameterized by the ratio of the tunneling between the diagonal and the edges of the underlying square lattice. And it turns out that the actual materials are located at ratios of these tunnelings which are actually higher than the isotropic triangular case. But nevertheless, the triangular isotropic lattice is very interesting to look at. And in the lab, so we get also snapshots of the density and spin distribution, and our main observable now is the spin-spin correlations among any kind of pair of sites in this lattice. So experimentally, what we observe in the square lattice is what I've shown a few slides ago, essentially antiferromagnetic Néel order, which is shown here as an alternation, a staggering of red and black and blue colors, which describe either anti-correlations or correlations between sites. And as you're changing the anisotropy towards a triangular lattice, you see that the range of these spin-spin correlations is strongly suppressed. And we only have correlations that are meaningful between nearest neighbors and next nearest neighbors in such lattices although the temperatures are relatively comparable between these two lattices.
You're saying you could achieve both ratios of T prime, both the one on the left and the one on the right?
Yeah, so this is experimental data. So we can achieve both ratios of T prime. And this is experimental data. And we can even, that's going to be the next slide, we can even tune continuously between the two extreme limits. And let me also mention that seminal work has been also performed in Peter Shaw's group at the University of Virginia, looking at triangular lattices and also observing nearest neighbor antiferromantic correlations. What we can do, again, a bit differently is the fact that we can tune the anisotropy between these two external limits and see, as a function of frustration, as it is gradually increased, how this spin order is killed off. And what you can also do, and that's maybe an observable which is more meaningful for condensed matter experimentalist theorists, is to take the Fourier transform of these real space correlations to plot the spin structure factor. And you can very neatly see that the symmetry of the spin structure factor is changing from a square geometry at the score. So you see spin structure factor peaking at the edges of this square Brillouin zone. And as you are increasing frustration, you see actually how this geometry stretches into hexagonal kind of geometry. And that kind of hexagonal geometry hints at what is called the 120-degree antiferromagnetic state. So essentially, that's the quantum, the ground state that you would expect for a quantum Heisenberg model at 0 temperature, where each of the spin is actually entire line to each other on a triangular plaquette with 120-degree related to each other. And although we don't exactly measure, the average angle between the spins, the symmetry is really strongly hinting at such a state here. What we can do even more interestingly is to change the doping. So essentially introducing some charged dopants in such systems in order to see how the dopants interact with these frustrations here, this frustrated order. And so that's easy to do by simply changing the number of atoms we load into these lattices. Here is plotted the next nearest neighbor correlations between neighboring sites as a function of positive or negative doping. So here, positive doping corresponds to adding more particles to the system. And we see, interestingly, that whereas the square lattice has particle-hole symmetry correlations at small dopings, the triangular lattice has very, very strongly suppressed AFM correlations as you're doping positively, well, doping with particles versus doping with holes. And what was even more striking when we saw that data in the lab was to see that at a very, very strong doping, so typically like above 20% or 50% in the triangular case, we even see the sign of these spin correlations reversing like towards high dopings, which hints at a possibly ferromagnetic phase of matter being produced in such a lattice. And so you can even look, in real space how the spin correlation map looks like. And again, on this point, you see red corresponding to red correlation corresponding to ferromagnetic correlations. Well, our temperatures are quite low and just low enough for quantum Monte Carlo simulations to actually reproduce our data, but we are really at the border of what quantum Monte Carlo can do such a system.
So your systems are finite size, right? But they're bigger, I think, than the section you're showing here. So this is averaged over several sites. The QMC, does it account for the inhomogeneity of the system, or does it assume you have a homogeneous?
Okay, so the question is whether the QMC, the numerical simulations, are capturing the fact that essentially experimentally we are loading atoms into a non-uniform lattice, and density is actually position dependent. No, the QMC data is actually on a uniform system. Nonetheless, because the spin correlation length is quite small, you could even consider, well, you could consider that local density approximation applies, and that the QMC is describing your data locally pretty well. Yeah.
So, Martin, could you clarify what portion of the data is experimental and what portion is quantum Monte Carlo?
The dots are experiment, And quantum Monte Carlo is this solid line.
And how do you measure the spin-spin correlation?
Sorry. To repeat the question, how do you measure spin-spin correlations and the spin structure factor?
Spin-spin correlations are obtained by essentially looking at these snapshots of either spin up or spin down or like density. And so there is, you can essentially expand, your spin-spin correlation function as a function of the density correlations that are actually measured in these snapshots. So you can, by performing some average of these snapshots, to get these spin correlations.
I see. But would it be true that you're, strictly speaking, measuring as Z instead of the transverse?
True. Yeah, I haven't specified that. Yes. So we are looking at spin up and down projected along a quantization axis, which is in our case SZ. So yeah, it's SZ correlations, and not like S.S correlations.
I see. Yeah. But would you agree that for some, like for instance, a neutron function could tell you that there is non-spin flip and spin flip scattering or channel and an experiment extremely important to distinguish the two. So if you want to look for like spin liquid, you actually want to measure S plus, S minus, not just as Z.
Yeah, that's a good point. Yeah, I mean, ideally, we are thinking about this, but ideally, you would like to be able to measure any say SX, SY, SZ kind of correlation. So that's something you could, in principle, think of by while using exponent techniques. I'm happy to discuss about, but yeah, that's one thing. Yeah. Good.
So the answer might be no, but is there an intuitive picture, an intuitive physical reasoning why particle-hole symmetry is broken here in the triangle, but not in the square?
Yeah, I mean, down the line, it really comes from the fact that the band structures are particle-hole asymmetric in the triangular case and symmetric in the square case. If you were to look at I'm coming to that actually right now. Yeah, but it's something you can already see from the density of state. Let me just emphasize in this case here that we are working in a regime where this ferromagnetic phase is not yet fully understood. But there are kind of limiting cases that are well known in the case of the Hubbard model where itinerant ferromagnetism can appear. And I'm going to quickly mention that also for the experts in the audience. One particular scenario where ferromagnetism can appear when you have interactions in a lattice in the mean field level is so-called Stoner ferromagnetism due to Stoner instability. Essentially, for weak interactions, provided that the density of state at the Fermi energy is strong enough, you could imagine a very small interaction energy between opposite spins to lift the degeneracy at the Fermi level and to fully polarize the system. And to answer Doc's question, here is the density of state plotted as a function of filling in the square lattice dashed lines versus the triangular lattice as a solid line. And you see actually that there is a Van Hove singularity occurring at positive dopings in the triangular case, which could explain this particle-hole asymmetry. Another reason why you could have this particle-hole asymmetry in another limit of very strong interactions is a so-called kinetic frustration, which, and maybe I'm going to be very fast on that, and I'm happy to answer more questions about it. You can essentially see it as some effect of constructive interference of a few dopants populating a given spin background as it is trying to delocalize over the entire background. And now the main difference between Hall and particle dopants is essentially the sign of the effective tunneling of that dopant on the lattice. So to be more explicit, a particle dopant can be considered as a normal particle and would hop around with a positive tunneling amplitude. And now if you're considering the simple case of a triangular plaquette, it can tunnel around the triangle 3 times with 3 positive tunneling elements, meaning that the entire, let's say the effective coupling between this state and that other state is positive, and you get you can see it as a kind of constructive interference between that state and the one where the particle has hopped 3 times, and that interference happens if you have a ferromagnetic background on the sites which are not doubly occupied. And so that's like a kinetic argument to explain why ferromagnetism might be favored when you have particle dopants. On the other hand, when you have a hold opened, the effective tunneling is negative, and so three hoppings around the triangular plaquette is going to, well, lead to an overall negative coupling to that state. But on the other hand, if you have an anti-aligned, antiferromagnetic configuration on the singly occupied side, you are going to get also next additional statistical exchange negative sites between these two extremal states, and minus signs conspire with each other to give you some positive interference. And so that negative tunneling amplitude is really what could explain why you get antiferromagnetism for very few hold opens in a system where you have very strong interactions. But of course, let me emphasize that this picture, these two pictures don't hold very well in this regime where we are at intermediate interactions, also in like temperatures which are comparable in our case to spin exchange energies, and with very strong dopings here, like 50%, where this like picture of single dopants, populating a single plaquette cannot really hold. And interestingly, it could be that this ferromagnetic phase is related to recent observations realized in transition metal dichalcogenides, so TMD moiré materials at Cornell 2 to 3 years ago, where they could see some hint of ferromagnetism in Curie temperature measurements at dopings which are, however, a bit different from ours. So it's pretty exciting to see how a cold atom quantum simulator can actually realize phases that are not so well understood and haven't been expected like from first principles by condensed matter theorists. Okay, so I've shown you now an example of such an exotic phase, which wasn't expected maybe theoretically and observed in experiment. I'm going to talk to you now about another kind of one-dimensional phase of matter, also relying on the quantum simulation of fermionic atoms, which are now not repulsively interacting as in the Hubbard model, but attractively interacting in a situation where atoms are actually populating a bulk continuous system. And the point of this phase and this work is to show that you can actually use new observables in order to probe exotic phases of matter. So the observable that we are looking at is here is transport. And so when you think about transport, the simplest experiment you can do is to simply take a voltage source and connect your favorite material to 2 points and to look at the current that's flowing through it. So it's the so-called two-terminal device. Inherently, this is an open system. If you look at this material here, you have electrons flowing in and flowing out, so it's an open system, which is something a bit weird to think about in cold atom systems, because, well, cold atom systems are intrinsically closed systems. They are like very well shielded into vacuum chambers and like very environment protected from the environment. How do you engineer your system in order to have an effectively open transport experiment? And so the answer relies on trying to introduce some separation of scale between the different parts of your cold atom system. If now I'm shaping my system such that the system of interest is much smaller than 2 reservoirs that are connected to it at 2 extremities, I could imagine a simple experiment where I'm populating one reservoir with more atoms than the other one, and then letting atoms flow from one side to the other, look by imaging after like a fixed evolution time, how many atoms have been transferred there, and essentially infer some transport coefficients such as conductance. In the lab, we're also relying on optical techniques in order to shape an elongated 3-dimensional cloud of lithium-6 atoms into such a system. So essentially pinching it into a 2-dimensional gas at the center, and then using now a microscope not to image, but to project a very narrow constriction that really reproduces, well, makes it the atomic equivalent of electronic heterostructure. And in addition, you can also sense through this microscope attractive beams that are essentially increasing the local density there, acting as the cold atom equivalent of a gate potential you would apply, on a normal heterostructure. And so now how do you demonstrate that such a narrow construction is actually 1D and is truly quantum? Like one hallmark experiment you can do is to look at conductance through that 1D wire and essentially look at conductance as a function of density. And we have been able to demonstrate a few years ago that conductance as a function of density or local chemical potential is quantized in units of 1/h, which is the cold atom, like the neutral atom equivalent of the E²/h quantum of conductance you have in condensed matter. And now, how do you make this maybe kind of boring one-dimensional construction? How do you turn it into a phase, a strongly correlated phase of matter with a lattice? Well, you're using very fancy holographic techniques relying on such a device called a digital micromirror device, which allows you to shape light arbitrarily and project it into a microscope in order to form kind of arbitrary potential inside this one-dimensional wire. And so here's how it goes. So here's a conductance curve of the device when you don't have any additional DMD, digital micromirror device potential applied to it. So conductance is simply increasing as a function of gate potential or density. And now as you're adding one bump, then kind of a quantum dot made of two bumps, all the ways to 9 period of a lattice, you clearly see this monotonic conductance curve turning into a non-monotonic conductance curve in blue, where essentially for intermediate densities, you have a local maximum, which is indicating a favored transmission through the lattice, which is essentially the equivalent of a band, probing the band of this lattice. Whereas at higher densities, higher, let's say, atom energies, you're probing a gap and see it as a decrease of the local conductance.
What's the lattice spacing?
The lattice spacing is about 1 micrometer. Yeah.
So the tunneling is very small, or you're in a shallow lattice?
That's a very good point. We are working in the shallow lattice regime. Lattice depth is typically of the order of 1 recoil energy here. So you can't really describe it as a tight bending lattice system that you would encounter in a Fermi-Hubbard system, but nonetheless, it's enough to probe some band and gap effects.
So this reminds me of the chronic penny type model. It's a one-dimensional wire with some profile. So everything. Would it be correct that the picture we see here would be what you would got from a chronic penny model, which indeed has gaps in the one particle spectrum, and if you tune chemical potential, you should see the non-monotonicity in the current. Can I think of it that way?
I mean, I think for any kind of periodic potential, you would expect a gap to appear. Maybe not at any like infinitesimal lattice height, but even describing this lattice as of course, it's a bit inhomogeneous here. But if you were to describe it as a sinusoidal lattice, like a normal 1D lattice, you would already expect at this the lattice depth we are using the lattice height to see a gap appearing in the band structure. So I don't know if I answered your question.
Martin, are these beams coming off at DMD?
Yes, these nine bumps are each created by the DMD. So we are controlling the exact number of bumps, like beams that are created on this channel by changing the pattern we have on this DMD. Yeah.
Is there any issue with interfering of the two wavefronts, or the wavefronts flat?
You mean the interference between? So this, like practically, this. If you were to look really optically, what's happening on the atoms there, the DMD is creating two. Well, after the microscope, two small beams, like finite waist beams, that are interfering at the center of the quantum point contact. So their interference is actually creating this one-dimensional lattice. If you were to look, say, at not the intensity as plotted here, but maybe the phase information, that's encoding in the light, each of these bumps has like 2 consecutive bumps have opposite signs, so you really get some kind of, well, it's not a standing wave, but a really like interference, like a really lattice which is created by interfering two beams together. Yeah. Okay. So far, what I've shown you so far was obtained with the weak interactions between the atoms, which makes it like pretty simple. You can really see it as the cold atom equivalent of a 1D semiconductor. What's interesting now is to crank up the attractive interactions between lithium atoms in order to see what's happening and see how strong correlations kick in. We measured a few years earlier in a simple quantum point contact without any additional structure that strong attractive interactions are actually making the conductance way more. And so the reason for that is as you increase interactions, attractive interactions, the two reservoirs as well as the central part is turning into a superfluid, which is strongly correlated, but essentially this superfluid character is going to increase transport very much across the construction. And so you see a smooth crossover from kind of a quantized conductance curve to something which is shooting up to many quanta of conductance as soon as you start populating the channel. On the other hand, what was surprising with the lattice is that we saw that this conductance curve as a function of density were practically independent of the interaction between the atoms, even in situations, these are the white points, where the reservoirs are strongly correlated unitary superfluids. And that took us by surprise to see conductance minimum that looks like gap feature fillings comparable to 2 particles per site. And so we attributed to this effect to an exotic 1D phase of matter that has been studied in quantum matter textbooks a few years earlier, which is essentially called a lithium emery liquid. I'm going to give you maybe a very naive and quick understanding of what's happening, but essentially, as you're increasing interactions between fermions of opposite spins inside a 1D wire, they will start to form pairs, which are made of two fermions. Now, provided that the interaction is quite large, and so these pairs don't overlap too much, you can really consider them as finite extent bosons, composite bosons, that are effectively repulsive. And the intuitive understanding for that is the fact that there is still some Pauli repulsion between the constituents of these pairs, and essentially the effective interaction between these composite objects is actually a repulsive, not an attractive one. And in the limit of diverging interactions, these form hardcore bosons, which is known to be mapping to free fermion model in 1D. And so as soon now as you are adding an extra lattice, turns out that any infinitesimal lattice depth, although we didn't try to observe that in the experiment, any lattice is going to pin the transport of these repulsive bosons in the 1D system and leading to a gap feature. And so that's one way to understand how this Luther-Emery liquid picture comes about in a lattice. That mapping, in general, is valid also for intermediate interactions where pairs are strongly overlapping with each other, and the mapping is only valid now in the case where you're essentially freezing your spin degree of freedom, and that only occurs when temperature is smaller than the one-dimensional superfluid gap in the 1D wire, which is the regime where we are looking at in the experiment.
Sorry, so Martin, this is at half filling, basically?
So it's different from the Hubbard model. It's a unit filling, or like 2 atoms up, down per site. So
the lattice is commensurate with the bosons, right?
It's commensurate with the bosons. Yeah. So it's let's say a unit filling for the boson. So yeah, to wrap this up, I hope I've convinced you today that cold atoms are a very good platform for performing the quantum simulation of condensed matter models, both to look at new materials and new observables, such as transport. And looking further in the future down the line, it would be very interesting to combine these two approaches of generating interesting materials and transport to essentially look at cold atom quantum devices, which would be very interesting to shed light onto doped phases of the Hubbard model. All this work wouldn't have been possible with an extraordinary teams of experimentalists and theorists. I'd like to especially thank Richard Scaletta, who helped us with these deterministic simulations for the triangular lattice project, as well as Thierry Giammarchi and Piotr Kryshins, who provided also theory for the 1D project. And of course, my teams, both at Harvard under the supervision of Markus Greiner and also in Zurich in the group of Tim and Singer. I'd like to thank you for your attention and I'm open to questions.
All right, thank you for that, Martin. Question?
Yeah, so for triangular, yeah, so for triangular lattices, I mean, there's various phases you can, get, right? You can have a stripe phase, you can have a new, the quantum spin lookup phase, as well as other phases, right? It solely depend on the exchange coupling between the nearest neighbor and the next nearest neighbor. I mean, it's not clear to me, which phase are actually you're seeing in.
You mean at half filling or at half filling?
Yeah, even half filling. I mean, depend on which type of order you have. Really depend on the exchange coupling ratio, right? Between the nearest and next nearest neighbor, right? Yeah. So first of all, how do you actually tune this? I mean, which phases are you seeing? It's not clear to me. Yeah.
No, it's not clear. I mean, I would agree with that. So what we only see experimentally is this kind of threefold symmetry in the spin structure factor, which I guess could be compatible with this 120-degree phase, but could be also compatible with more complicated phases of matter.
So it's a new order phase.
So not clear. What I can say, confidently, is that we see signatures that haven't been observed, earlier on in Hubbard lattices, at least with cold atoms. I'm not, confident to put an exact label in that phase. I mean, this 120-degree phase is just a hypothesis, like a likely hypothesis. About your comment about the next nearest couplings, in our case, I mean, we are using lattices where you can safely neglect those. So
it's only nearest neighbor.
It's only nearest neighbor, yeah. And so with only nearest neighbors, quantum Heisenberg model, it's kind of known that in the ground state it's 120. And it's also expected, now it's a bit more complicated with the Hubbard model because you can also change the ratio between U and T, and the ratio U over T. So it's supposedly also, I mean, many numerical results converge to say that this 120-degree phase is the one that you would expect in the ground state, down to interaction strengths of about U over T of 9 or 10, so like intermediate regimes. Yeah.
So in the second part, in the transporty part, I was wondering whether, rather than putting in a lattice, if you really, you talked about effectively making a dot, right? I mean, if you can make a dot and you can put attractive interactions on the dot, then you can, in principle, there's a lot of work that was done a long time ago on negative U centers, right? Which is basically this idea that I have some magic site where the U is negative, so I have a real attractive, two-particle attractive interaction on that site. Okay. I don't know, is that something that you can actually try and implement, or?
So now your attractive interactions are coming from, would this attractive interaction be also already present without the dot, or is it just the presence of the dot?
I think the toy model is that you have, your interactions are very, very weak everywhere except on the dot where you make the interaction strong and strong. You make the interaction strong and attractive.
That's an interesting question. I mean, I think overall in cold atom experiments, it can be a bit tricky to, okay. Yes, I mean, in principle, due to additional confinement, you could make the effective interactions much stronger there. You can't easily tune, say, the scattering length or like in a position resolved way with coordinates, unless you were to maybe rely on well, something that Randy has looked at too, confinement-induced resonances, or maybe looking at the effect of this additional confinement, transverse confinement, that could somehow shift the position of these Feshbach resonances and change a bit, locally the 1D interaction strength. But yeah.
So on the triangular lattice experiment, you see 120 degree as you rotate around the three sites, 120 degree angle between the spin projections. Could you explain that, maybe?
So what we observe is that kind of threefold symmetry of or sixfold symmetry of the spin-spin correlations in real space. And again, spin-spin being SZ. So we haven't, tried to look at any other kind of like SX, or SY correlations, because we assume here that the system is SU2 symmetric.
Okay. How do you know that the spin isn't canted out of the plane?
We don't know. We don't know exactly. So it's, I think, yeah. I would say it's a hint that we have some phase of matter which has let's say a 3 sublattice kind of order.
Okay.
But the exact nature of this order, whether it's a planar order or like a out of the plane kind of order, is still open.
Okay. Yeah, Matt.
So with respect to Luther-Emery, can you tune away from commensurate filling? And if you tune away from commensurate filling, do you see superfluid behavior again? And the second part of the question is, Luther-Emery is supposed to be a charged Luttinger liquid and spin Mott insulator. So is there a way to show or detect that the spin degrees of freedom are gapped here?
So about your first question, yes, we are tuning away from commensurability by changing this gate potential. So essentially, we have two atoms per site here, one there and 0 down here. And yeah, indeed, as we are increasing the density above 2 particles per site, we actually start to see this conductance shooting up, so indicating there that we have superfluidity. About your second question on the spin gap, I mean, actually, I should turn to Randy. You can also devise some Bragg spectroscopy probe in order to look at the local spin order, and yeah, just look at spin order there, spin gap there. Yeah.
So theory is conspicuously absent on the right. Has anyone tried to calculate this, or are there reasons it's especially difficult?
I haven't shown it here out of just to make the plot visible, but so Thierry Giamarchi and Piotr Grishins have been able to capture, devise some equation of motions for the charge degree of freedom, assuming that the spin degree of freedom is totally frozen. And in a 1D geometry, look at the evolution of let's say, a given gradient in the density and see how that evolved. And essentially reproducing this dip in conductance around fillings of 2 particles per site. Yeah, here the minima are maybe a bit shifted in this kind of plots because we are not plotting, conductance as a function of density, but chemical potential. And so depending on the exact equation of state and the interactions, you you have like a nonlinear mapping between the two. But that's pretty well reproduced here by that theory. Yeah.
Okay, it's been very interesting to hear your work, Martin, and to ask you, all these questions. I know we ran a little bit late, but mostly it's because of our fault that we asked a lot of questions that are interesting. So let's thank Martin.